Lesson: Time Series Analysis, Models and Applications for Demand Prediction. Time series analysis represents a powerful tool in demand forecasting, offering actionable insights and practical applications for AI-driven supply chain analysts. The intricate patterns and trends inherent in time series data allow for nuanced predictions that can significantly enhance the efficiency and responsiveness of supply chain operations. Understanding time series analysis empowers professionals to apply mathematical models and frameworks that capture the temporal dependencies and seasonal variations often present in demand data. At the heart of time series analysis lies the ability to model temporal data to discern patterns that inform future demand. The Autoregressive Integrated Moving Average model is a staple in this domain, renowned for its applicability in various demand forecasting scenarios. ARIMA models are constructed by integrating three components: autoregression, differencing, and moving average. The autoregressive component relies on the dependency between an observation and a number of lagged observations, while differencing is used to make the time series stationary, and the moving average component models the relationship between an observation and a residual error from a moving average model applied to lagged observations. This model is particularly useful in cases where the data shows evidence of non-stationarity, and it can be tailored to fit specific demand patterns by adjusting its parameters accordingly. The seasonal decomposition of time series is another pivotal method, especially when dealing with data exhibiting strong seasonal patterns. STL decomposes a time series into seasonal, trend, and residual components, providing a structured way to analyze and interpret the underlying factors driving demand. This decomposition is invaluable for identifying seasonality and adjusting forecasts to reflect seasonal variations accurately. By understanding these decomposed components, supply chain analysts can develop more refined forecasts, enhancing their ability to predict demand fluctuations with greater precision. Practical application of these models often involves the use of computational tools such as Python, which offers libraries like stats models and pandas for time series analysis. These tools facilitate the implementation of ARIMA and STL models, allowing for the exploration and visualization of demand patterns. For instance, by using the stats models library, professionals can fit an ARIMA model to historical demand data, conduct diagnostic checks, and generate forecasts, all within a streamlined workflow. This hands-on application ensures that theoretical knowledge is translated into practical skills that can be directly applied in real-world supply chain scenarios. Expanding beyond traditional models, machine learning approaches such as long short-term memory networks are gaining traction in time series forecasting. LSTMs, a type of recurrent neural network, are specifically designed to capture long-term dependencies in sequential data, making them particularly well-suited for complex time series with intricate patterns. By leveraging LSTMs, supply chain analysts can model nonlinear relationships in demand data, yielding forecasts that are adaptive to dynamic market conditions. Implementing LSTMs requires a robust understanding of neural network architectures and the ability to tune model parameters to optimize performance. Libraries such as TensorFlow and Keras provide the necessary infrastructure for building and training LSTM models, enabling analysts to harness the power of deep learning for demand forecasting. A compelling case study illustrating the efficacy of LSTM models in demand forecasting is provided by Salinas et al., where the authors applied an LSTM-based approach to predict product demand across multiple retail outlets. The results demonstrated significant improvements over traditional methods, with the LSTM model capturing complex demand patterns that were previously unrecognized. This case underscores the potential of integrating machine learning techniques into time series analysis to enhance forecasting accuracy and inform strategic supply chain decisions. In addition to these advanced techniques, the application of time series analysis in demand forecasting often involves addressing common challenges such as data quality, the incorporation of external variables, and the management of uncertainty. Ensuring high-quality data is paramount, as inaccuracies or inconsistencies in historical demand data can lead to erroneous forecasts. Data preprocessing steps such as outlier detection, missing value imputation, and normalization are essential to maintain the integrity of the analysis and ensure reliable predictions. Incorporating external variables, such as economic indicators or weather data, can further enrich time series models. These covariates can provide additional context and improve the model's ability to capture demand drivers that lie outside the usual historical patterns. Techniques such as vector autoregression allow for the integration of multiple time series, facilitating the modeling of relationships between demand and external factors. This holistic approach enables supply chain analysts to build more comprehensive models that account for a wider range of influences on demand. Managing uncertainty is another critical aspect of time series analysis in demand forecasting. Probabilistic forecasting methods, which provide a range of possible future outcomes along with their associated probabilities, can be particularly useful in this regard. These methods allow for the assessment of forecast uncertainty and the development of contingency plans to mitigate potential risks. Tools such as Monte Carlo simulations can generate a distribution of possible future demand scenarios, enabling supply chain analysts to evaluate the robustness of their strategies under varying conditions. In conclusion, time series analysis offers a rich toolkit for demand forecasting, with models and applications that can be tailored to the specific needs and challenges of supply chain operations. By leveraging ARIMA, STL, LSTM models, and integrating external variables, supply chain analysts can enhance their forecasting capabilities and make data-driven decisions that optimize performance. The practical application of these techniques using computational tools like Python, TensorFlow, and Keras ensures that professionals are equipped to address real-world challenges and drive improvements in supply chain efficiency. As the field continues to evolve, staying abreast of the latest advancements in time series analysis and machine learning will be essential for AI-driven supply chain analysts seeking to maximize their impact.